So now I want to introduce something slightly different, which is the pigeonhole principle. And the pigeonhole principle is an extremely simple fact, but it is an idea that can be used in very clever ways to prove nice things. So I'll try to give a little example of both of those things, but we'll talk more about it next time as well. So the pigeonhole principle says if n plus 1 pigeons are arranged in n pigeonholes, then, regardless of how you try to arrange them, some hole must contain more than one pigeon. So it's you know, in this formulation, it's pretty clear, right? If you have more pigeons than holes, then some hole has to have more than one pigeon in it. Fair enough. Actually, this thing has an analog with sets as well, which is that if you remember when we talked about cardinality, there exists an injection from a set A to a set B if and only if the cardinality of A is less than or equal to the cardinality of B. So the pigeonhole principle is basically saying that if the number of pigeons is greater than the number of pigeonholes, then there is no injection. And having it not be an injection, remember this means that some point has more than one preimage, and that is corresponding to more than one pigeon going into that pigeonhole. So what's an example of this? A very simple example is, let's look at the participants in this lecture. There are 13 participants. I guess technically that includes Sander and also Sander's iPad, but let's not worry about that. Let's just say there's 13 people in lecture. And 13, actually, you know what? That's equal to 12 plus 1. Not only is it bigger than 12, it's actually 1 more than 12. And there's 12 months in the year. So by the pigeonhole principle, there must be some, must be some pair of people in this lecture who were born in the same month. So in this example, the pigeons are people, and the pigeonholes are birth month. And since there are more people than birth months, it must be that there is some birth month with more than 2 people in it. So this is, you might almost want to say this is obvious, although without thinking about it, maybe it's not obvious. But now that you've thought about it, maybe it's obvious. So let's see an example of applying the pigeonhole principle in a slightly more clever way. And the cleverness basically comes down to realizing that the pigeonhole principle is applicable and figuring out the right idea of what are the pigeons and what are the pigeonholes. And then you might have to do some counting there as well to show that you get what you want. So claim any graph. So again, we're going to come back to graphs at the end of the course, but they're just so good for examples, so I can't help it. Any graph has two vertices with an equal number of edges. So again, what is a graph? A graph is some collection of nodes or vertices with edges between them. Something like this. So in particular, no loops or double edges. So nothing like this, that's a loop, and nothing like that, that's a double edge. None of that, just some plain old vertices, some plain old edges. So let's check this. Actually, I guess we just drew a little graph here. In this example, there are many vertices with the same number of edges. All of these vertices have two edges attached to them. And all of these vertices have one edge attached to them. So it checks out in that we didn't try very hard to find a counterexample, but checks out in this case. But okay, let's prove it. How do we prove this? So let n be the number of vertices. Then every vertex has some number of edges. And what are the possibilities for that number? Well, it could be 0. If you put a vertex just out of nowhere with no edges connecting to it, you can have 0 edges like that. Let's do that. I'll just leave one there. So you can have 0 edges or 1 edges or 2 edges, etc., up to n minus 1. Right? Because since we're outlawing loops and double edges, the maximum number of edges is you can be connected to all the other vertices. And there's n minus 1 other vertices besides any particular guy. So this is n possibilities. By which I mean this is n different things that you could have. But so we're going to have to do a little more work, because you can start to see the outline now that what is going to be the pigeons and the pigeonholes. So the vertices are going to be the pigeons, and the number of edges that they have, the different possibilities for the number of edges, are going to be the pigeonholes. Because to show that some pair of vertices has an equal number of edges basically means that some pair of vertices falls into the same pigeonhole in this sense. But we haven't gotten that yet because we have n vertices and n pigeonholes, which is not good enough. But notice that 0 and n minus 1 can't both happen. because this means this is a vertex with no connections, and this is a vertex connected to every other vertex. So in particular, this guy is saying that he's not connected to this guy because he has no edges. And this guy is saying he is connected to this guy because he has all the edges. So they can't both happen at the same time. So, in fact, there are n-1 possibilities. So by pigeonhole, there must be a pair of vertices with the same number of edges. So I feel like this is a nice example of, the Pigeonhole principle itself is fairly simple, but finding clever ways to apply it can be used to prove pretty non-obvious things. But more on that next time.